Welcome to this explainer. If you're sitting inside a modern building right now, there is a literal high-stakes balancing act keeping the roof over your head. It's the tension between the quick human eye and the totally unforgiving math of structural engineering. Today, we're exploring that fascinating dynamic that exists on every major construction site, the difference between a rapid visual estimation and strict code compliance when it comes to rebar placement. Let's just jump right in. We're putting the fast, gritty reality of the job site right up against the meticulous demands of engineering codes. On one side, you have the 1-second visual scan, a quick field assessment. On the other, you've got the mandatory formal inspection, which is driven by exact measurements and detailed structural drawings. Both are absolutely essential, but they serve very different purposes in making sure our buildings don't, fall down. So you might be wondering, why does a simple 1-second glance at a rebar grid even matter when we're building these massive, highly engineered structures? Why not just rely totally on the formal inspection? Well, let's set the stakes here and look at what happens when things go wrong before the inspector even gets their tape measure out. And the concept of honeycombing brilliantly illustrates exactly why we care. When rebar is placed way too closely together or it gets heavily congested, it acts just like a sieve. It literally blocks the aggregate rocks in the concrete from flowing around the steel. The result? You get these dangerous hidden voids inside the concrete that fundamentally destroy the structural integrity. It's kind of like trying to pour chunky soup through a fine strainer. That visual check is our very first line of defense to make sure the concrete can actually flow properly. And the consequences? They are severe. As the structural experts at Bayou City Steel note, improper placement doesn't just look sloppy on the site, it permanently weakens the building. Whether that's reduced concrete cover, leaving the steel exposed to the elements, or structural weakness from bad spacing, the end result is compromised durability and some incredibly costly repairs down the line. Let's move into the rule of thumb for rapid assessment on the job site. There is a stark contrast between a correct grid with beautifully even spacing and an incorrect grid, showing what we call spacing drift. In just 1 second, a trained eye can instantly spot where those bars are bunching up or drifting apart. That visual anomaly is a massive red flag indicating the structural plan has just been violated. So what's a trained inspector actually looking for during that quick 1-second pass? It's a mental checklist of red flags. They're scanning for spacing drift, cover violations, unsecured bars that might shift around, and lap splice crowding, which is where way too many bars overlap in one single spot. Any of these issues means the concrete pour needs to halt immediately. Let's break down that first red flag, spacing drift. The crucial thing to understand here is that it's often caused by poor tying. If tie wires are loose, missing, or just inadequate, the heavy vibration during the concrete pour will shift the entire grid. Even if it looked perfectly fine beforehand, that sudden movement instantly violates the structural plan, leading straight to that dangerous honeycombing we talked about. Another massive red flag: cover violations. Concrete cover is simply the distance between the rebar and the outside surface of the concrete. If the rebar is sitting too close to the earth, say less than the required 3 inches, or too close to the exterior forms, that is a critical failure. Without enough concrete cover, the steel gets exposed to moisture, and that accelerates corrosion. And as steel rusts, it actually expands, literally blowing the concrete apart from the inside out. All right, time for a reality check on the mandatory formal inspection, because while the eye is super fast, the engineering code is absolute. Here is the absolute fundamental distinction between a quick estimation and strict compliance. A fast glance? Sure, it might save you from a glaring disaster, but final approval must always rely on physical measurement. At the end of the day, someone still has to break out the tape measure to painstakingly verify the bar diameter, check the actual lap splice lengths, and guarantee the minimum clear spacing is mathematically spot on. And the math gets incredibly specific. According to the ACI code, the minimum clear spacing between parallel bars isn't just a random guess. It has to be at least 4/3, or roughly 1.5 times, the maximum aggregate size of the concrete. This exact ratio guarantees that the gravel in the wet concrete can physically pass right between the bars without getting stuck. Now let's look at code compliance versus estimation, where things get really black and white. True compliance requires following a formal engineer-approved layout. For example, a blueprint for a beam will dictate the exact bar sizes, the exact 80mm spacing between the layers, and the exact cover. When the formal inspection actually happens, the physical reality inside that wooden formwork has to match the drawing down to the millimeter. There is zero wiggle room. As industry resources like the Tool Grit guidelines remind us, generic digital calculators are awesome for quick arithmetic or getting a rough idea of your steel area. But they absolutely do not account for complex load paths, seismic detailing, or specific crack control criteria. The required minimum steel and spacing always has to come from the governing, approved engineering drawings, period. So, how do we bridge this massive gap with AI verification? How do we combine the lightning speed of a visual scan with the meticulous precision of a tape measure inspection? The answer is coming from the bleeding edge of construction tech, with platforms like SteelCheck. It uses GPU-accelerated computer vision to verify steel sizes, placement, and compliance in real time. It effectively gives a camera the trained eye of a master inspector, but backed by the mathematical precision of the engineering code. The specs on this are frankly wild to think about. We're talking about a staggering 99.4% detection accuracy in under 2 seconds. It literally identifies sub-millimeter deviations, making inspections up to 10 times faster. This kind of AI completely removes the subjectivity, and let's face it, the exhaustion of manual human inspections, while ruthlessly enforcing the rigid boundaries of the ACI code. The workflow seamlessly merges the visual with the formal in 3 simple steps. First, you just capture the visual data on a mobile device, right there in the dirt. Second, the AI instantly compares that physical reality against the highly detailed BIM specifications. And third, it reports automated compliance. It spots that spacing drift or the cover violations before a single drop of irreversible concrete is ever poured. It's a pretty incredible evolution from the humble tape measure, right? And it leaves us with a really provocative thought to end on today. As this technology bridges that crucial gap between a rapid human estimate and absolute code compliance, will the next skyscraper you stand in rely entirely on artificial intelligence to verify its hidden steel skeleton? Thanks so much for joining me on this explainer. I hope you found this deep dive as fascinating as I did.